Welcome to the deep dive. Today, we're digging into something really fundamental that's quietly holding back even our fastest computers. It's all about how quickly they can grab and store information. Most tech, from your phone to massive data centers, uses this old design, the von Neumann paradigm,
That's right.
and it creates this bottleneck, a data traffic jam.
Exactly.
And with AI and machine learning exploding, well, they need huge amounts of data fast. It's becoming a real problem.
A critical one.
So our mission today, how do we break that bottleneck? How do we build the super efficient hardware that these hungry AI systems really need?
And that leads us straight into next-gen memory. We're going to focus on two really promising technologies. Phase change memory, PCM for short,
Okay.
and something called ovonic threshold switches, or OTS. We'll unpack the science, look at the huge potential, but also the challenges that have kind of held them back.
Challenges are important.
Crucially, yeah. And we'll talk about the recent breakthroughs that are finally starting to change things.
And as always, we're pulling this straight from the latest research, giving you the inside track on the tech that's shaping tomorrow. Ready to jump in?
Let's do it.
Okay, so this von Neumann bottleneck, let's break that down a bit more. It's basically because the processor, the brain, is separate from the memory, right? The storage.
Precisely. They're constantly sending data back and forth. Think of it like a super fast chef
Okay.
who keeps having to run across a massive kitchen to grab ingredients from the pantry. No matter how fast the chef is, those trips slow everything down.
That makes sense. That constant back and forth, that's the bottleneck.
Exactly. And it's a killer for AI and machine learning, which just devour data.
Yeah.
We're talking petabytes for training, real-time processing.
Wow.
Yeah. Traditional memory, especially non-volatile memory, the kind that remembers when the power is off, it just can't keep up efficiently. It throttles AI's potential.
Right. So you need faster non-volatile memory, and that's where this idea of in-memory computing comes in.
Spot on. Instead of moving the data to the processor, why not bring the processing to the data?
Like putting a mini prep station right inside the pantry.
Perfect analogy. It cuts out all that travel time. And that's where technologies like PCM and OTS, especially in these dense cross-point arrays,
Yeah.
become absolutely vital.
Okay, let's get into those. PCM first. Phase change memory. What's the core idea?
Okay, so PCM uses these special materials, chalcogenide compounds. Think alloys like germanium, antimony, tellurium, GeSe is the common one.
T, got it.
Or sometimes more complex ones like GeAsSeTe, which includes arsenic and selenium.
And what do these materials do?
The really cool part is they can switch between two states.
Mm-hmm.
An amorphous state, think disordered atoms like glass, high electrical resistance.
Okay, high resistance, disordered.
And a crystalline state,
Mm-hmm.
atoms neatly ordered like metal, much lower resistance.
Lower resistance, ordered. And you can switch between them.
Yep, using electrical pulses. A specific pulse, a set pulse, heats and cools it slowly, letting it crystallize. Low resistance.
Set means crystalline, low resistance.
Right. Then a reset pulse, shorter, stronger heat, melts it. And it cools super fast, freezing it in that disordered amorphous state. High resistance.
Reset means amorphous, high resistance. And it stays like that,
Yeah.
even with no power.
Exactly. That's the non-volatile part. High resistance or low resistance, it holds that state. That's your 0-1 for data storage.
Fascinating. Okay, so that's the memory cell. But you mentioned these dense cross-point arrays. How do you make sure you only write to the cell you want? Isn't there a risk of, accidentally changing the neighbor's crosstalk?
Excellent question. Yeah, that's a huge issue in dense arrays. Imagine that city grid again, applying voltage to one street and one avenue.
You only want the intersection.
Right, but current could leak down other paths, sneak paths, messing things up, wasting power. That's where ovonic threshold switches, OTS, are critical.
The other key player, OTS.
Yeah, they're basically very smart, very precise gatekeepers, selector elements. They sit with each memory cell.
How do they work?
They're two-terminal devices. They block current completely until you hit a specific voltage, the threshold voltage, or ETH. Then, bang, they switch on sharply.
So they only let current through when you apply enough voltage exactly where you need it.
Precisely. It ensures only the selected cell gets the current pulse, minimizing leakage and power waste in the rest of the array. Really high selectivity.
And this isn't just lab stuff, right? I think I've heard of this.
You probably have. Intel and Micron's Optane memory. That used OTS selectors. It showed this approach works in real high-performance products.
Right, Optane. Okay. So the concepts are solid. PCM stores, OTS selects. Why isn't this everywhere then? What's the hurdle?
Ah, the billion-dollar question. It comes down to manufacturing, specifically scaling up in 3 dimensions, 3D integration.
Meaning stacking layers?
Exactly. We need incredible memory density now. Think
Yep.
ultra-large-scale integration.
Yeah.
You can't just spread memory out flat anymore. You need to build upwards. Sophisticated 3D stacks, vertical arrays.
Like we already see with NAND flash and SSDs, right? Those have hundreds of layers sometimes.
Precisely like that. Building skyscrapers of memory. That's the kind of density PCM and OTS need to compete. But building those skyscrapers with these specific chalcogenide materials, that's been the challenge.
Why? What's so hard about it?
It's a problem called conformality. Traditional methods for depositing thin films, like physical vapor deposition or PVD,
TVD, okay.
they're okay for controlling the material's composition, but they struggle to coat complex 3D shapes uniformly. Imagine spray painting that jungle gym you mentioned earlier.
Right, you'd get thick paint on the easy-to-reach bars, but barely any inside the tight corners or deep down.
Exactly. PVD films often end up thin or non-existent at the bottom of deep trenches or on vertical sidewalls in these 3D structures. And if the film isn't uniform, the device won't work reliably or at all. PVD just fails in providing the conformality required for these high-density 3D arrays.
So that was the roadblock, getting these amazing materials into these complex 3D structures perfectly uniformly.
That was the core challenge, holding back widespread adoption for years. How do you coat every nook and cranny of these microscopic skyscrapers perfectly?
Okay, so how did they solve it? There must be a better way.
There is. The solution lies in a technique called atomic layer deposition, or ALD.
ALD, heard of it, but what makes it different?
ALD is completely different from PVD. Instead of spraying material, it uses a sequence of chemical reactions. You expose the surface to one gas, it reacts, you purge it, then expose it to another gas, it reacts with the first layer, purge again. You build the film literally one atomic layer at a time.
Wow, atom by atom.
Pretty much. It's incredibly precise, and because the reactions happen on all exposed surfaces, you get fantastic conformality. Perfect uniform coating even in deep trenches and complex shapes. Atomic control over thickness, too.
That sounds perfect for the 3D problem. So why wasn't ALD the immediate answer for chalcogenides, if it's so conformal?
Ah, well, that's where the specifics got tricky. Even with ALD's promise, making high-performance chalcogenide devices, especially OPS, using ALD proved really difficult for a long time.
What were the hurdles within ALD?
Several things. First, early ALD work often resulted in binary films,
Yeah.
2 elements. But for the best performance, especially stability, you really need more complex alloys, 3 or more elements.
Like that GS material you mentioned earlier, with arsenic.
Exactly.
Yeah.
Arsenic, in particular, was known to be key. Adding arsenic improves thermal stability, stops the material crystallizing when you don't want it to, and leads to really stable, high-endurance selectors.
Wow.
But there just wasn't a good ALD process for arsenic-containing chalcogenides.
Okay, so getting the right ingredients in was hard. What else?
Well, even getting uniform composition with the available chemical precursors was tough. And the material you were trying to grow on the substrate often affected how well the film grew. It wasn't straightforward. These issues basically capped the performance you could get from ALD chalcogenides for a while.
So ALD was the key, but it had its own set of problems with these specific materials. Sounds like a real puzzle.
It was, but this is where the recent breakthroughs come in. Researchers got really clever with ALD strategies.
Tell me about them. What did they figure out?
Okay, so one major advance tackled that arsenic problem for OTS. They developed something called a GeSe heterojunction OTS.
Heterojunction, like a layered structure.
Precisely. They figured out they could first deposit a super-thin conformal layer of germanium selenide, GeSe, using ALD. This layer then acted as a perfect starting surface, a highly reactive base, for the next ALD step involving arsenic and tellurium precursors.
So the first layer kind of prepped the surface for the trickier arsenic stuff.
You got it. It allowed the arsenic telluride, ACE2TE3, to nucleate properly, enabling them to finally create those high-performance GeAsSeTe films using ALD. It was a really smart workaround.
Brilliant. And did it work? What were the results?
Fantastic results. They achieved excellent conformality, literally unity step coverage, perfect coating even inside structures with a 20-to-1 aspect ratio, like coating the inside of that super long, thin straw perfectly.
Wow.
And the film composition was consistent through performance-wise. Very low leakage current, about a nanoamp. A nice clear threshold voltage around 3 volts.
Okay, low power, clear switching. What about speed and endurance?
That's where it gets really exciting. Switching time, around 2 nanoseconds.
2 billionths of a second.
Insanely fast. And endurance. It exceeded 10 to the 9 cycles. A billion
The
cycles.
billion switches. That's incredible durability.
It is. Plus, very stable performance over time, low VTH drift. It showed you could make highly stable, fast, low-power arsenic-containing OPS using ALD. A huge step.
That really cracks the selector problem for 3D. Amazing. But you mentioned two breakthroughs. What was the other one?
The other focused more broadly on controlling the composition of GeSe germanium antimony tellurium using ALD, allowing them to make both OTS and PCM devices.
So fine-tuning the recipe for different jobs?
Exactly. For OTS, they made GeAsSeTe 4 devices. They showed fast switching, around 13 nanoseconds. Still very fast, though these particular ones had a bit higher leakage current than the gassed ones. It shows there are often trade-offs in material science.
Right. Optimizing one thing might affect another. What about the PCM they made with ALD?
That was really impressive. They focused on G2SB2T5, the standard PCM material, but made with ALD. It showed the typical sharp switching behavior, around 1.4 volts.
And the performance.
Really strong. A wide memory window, meaning a big difference between the high and low resistance states over 2 orders of magnitude, making it easy to read the data reliably. Write times were short, around 100 nanoseconds, and it needed quite low current to switch, a low reset current density.
How did it compare to the older PVD methods?
This is key. The results were matching or improving over state-of-the-art PVD PCM devices. So ALD could now perform just as well or better. Plus, it had that crucial conformality advantage for 3D.
That's a big deal. Better performance and suitable for 3D.
And compared to previous ALD PCM efforts, this new work showed crystallization times 10 times faster and a memory window 10 times wider. They also showed it could cycle reliably 1,000 times. It really elevated the state of ALD PCM.
Okay, so these breakthroughs are huge. We have ALD methods now that give us the conformality for 3D and the performance needed for both the memory cells, PCM, and the selectors, OTS. So, back to the earlier question, why isn't this tech flooding the market right now? What's the holdup?
It really boils down to the difference between a breakthrough in the lab and full-scale, cost-effective manufacturing. These studies, they open a new route, they pose the foundations.
They prove it's possible.
Exactly. They overcame the fundamental technical feasibility hurdles for making high-performance multi-element chalcogenides conformally in 3D using ALD. That was the wall that stood for years. Industry couldn't really invest heavily until those core fabrication problems were solved.
So the science is now catching up to the potential.
Precisely. But now comes the engineering and economics. Scaling these specific ALD processes up to high-volume manufacturing, ensuring yield and reliability across billions of devices, integrating them into existing production lines. It takes enormous time and investment.
Years and billions of dollars, probably.
Absolutely. Plus, you're competing against entrenched technologies like NAND and DRAM, which are also constantly improving and benefit from mature, massive manufacturing infrastructure. So the path from these foundational breakthroughs to seeing ALD-based 3D PCM OTS in your devices is still a significant one. But the key scientific barriers have been overcome. The potential for ultra-high-capacity 3D chalcogenide memory arrays is now much more real.
Okay, so it's not an overnight switch, but the path is clearer now than ever before.
Definitely. And the impact is potentially massive. These advancements are truly pivotal. They're paving the way for next-gen memory that could finally help us break that von Neumann bottleneck and really unlock the next level of AI performance. Faster, denser, more energy-efficient memory. It changes the game.
So what we've explored today isn't just some obscure lab curiosity. It's the groundwork for the future of computing, happening right now at the atomic scale.
That's the takeaway. It's the fundamental material science that enables those headline-grabbing advances in AI and high-performance computing down the road.
You've just had a deep dive into that foundational work. Understanding this gives you a real insight into where things are headed.
And remember, knowledge is powerful. Understanding these shifts helps you appreciate how our devices will become faster, smarter, more capable, all thanks to manipulating materials layer by atomic layer.
So here's a final thought to leave you with. If controlling atoms like this can revolutionize memory and computing, what other everyday things around us are just waiting for their own material science breakthrough to unlock some completely unexpected potential? Something to think about.